All right, so we're now looking at another demonstration problem right here. So boarding for a Ferris wheel occurs on a platform next to the 6 o'clock position. See the image. So this is the picture over here. Okay, so the 6 o'clock position is down here, and the picture, according to the picture, this platform is, the ground is right here. This platform is 12 feet above the ground. So this is where any rider would board onto that Ferris wheel. Okay. Now, so the next information, the Ferris wheel makes one full revolution every 5 minutes. So meaning one full revolution means, let's say for that passenger, for that rider, once he boards on that the cart right here, it's gonna make one complete rotation and comes back to that same point in every 5 minutes. Now let's assume that the Ferris wheel never stops rotating, meaning you know they won't stop to wait for the rider to hop in. It just continuously runs and runs and runs, and riders just need to be as fast as possible to jump on, to hop onto each of the carts right here. And so the Ferris wheel reaches a maximum height of 100 feet above the ground. So, and a minimum height of 12 feet above the ground, which is right here, is the minimum height right here, because it's exactly 12 feet according to the picture right here. And so according to this information, the highest point is up here, 100 feet above the ground. So the ground is down here 100 feet above the ground. And then the lowest point is 12 feet above the ground. So now with this problem right here, let t equals 0 correspond to boarding the Ferris wheel from the platform. So now I brought in this demonstration problem to see how we can align so that I can reinforce how I use that general guideline I pointed out earlier. Okay, and so what I would do first, I'm going to recognize the highest value or the highest point and the lowest point. Okay, so think about, if we completely ignore the rotating nature of that Ferris wheel right there, then observing a rider, any rider, this is what he's doing. He goes from low, starts, goes high and swing back down low, goes high and swing back down low periodically. And that's why, to me, the way how I would approach it, first thing, I would set the highest point. And we already learned that from the wording description. That's 100 feet above the ground. And then I set the lowest point down here. That's 12 feet above the ground. All right, and so exactly halfway middle between highest point and the low point right here, that's where we put our center line. And this is also our the time axis right here, t. And the height is this axis h. And so we can, with a little math right here, with some quick math right here, we can find out that the mid height right here has to be 56 feet above the ground. Okay, so that's the mid height right there, and this will eventually be our center line, but we will get to that. So just to align with my guidelines right there, I set the high, I set the low, I put the center line right exactly in the middle between the high and the low. Okay, and the next step now is to look for, either we choose a starting point from the given data, or we can look for a given starting point, a starting point that's given from the data. Okay. And so now back to the wording of the problem right here. This statement right here is indicating for us that we have a given starting point. So we cannot choose in this case, but we have to take this starting point here as a given point. So let t equals 0 correspond to boarding the Ferris wheel from the platform. So that means it's starting at this point right here. But that means we're starting at the low. We're starting at the low being the 12 feet low right here. And then once boarding, the rider will keep rising at his heights to the maximum height being 100 feet. And then come back down to 12 feet again, being the low. And then the midline right here, the mid height right here, the middle height is exactly at 56 that we have shown on the board. All right, and so in that way over here, we recognize, and that's also leading into putting in the plotted data points right here. So the start, you can just call that start right here. That's where we start. T equals 0 is here. But we're starting at 12 feet above the ground. So it's down here. Right? So T equals 0 is right here. And then at that starting point, we start at low. Okay? But now, again, the Ferris wheel completes one full cycle every 5 minutes. So if we call this a 0 over here, we can just set that space right here, that scale right here, we call that T equals 5. And from T equals 0 to T equals 5, that's one complete period. So we have one period in here. So we start slow, then at that ending point right here, we have to also end up at low again. Okay? That's how I'm plotting in the given data point right there. Okay? Because this was not directly mentioned, but we know it has to be like that. It's because it's periodic. Okay? It's going in a cycle. So every 5 minutes, it's going to come back to that exactly same point right there. Okay? Now, when we're looking a little more closely at the wording of this problem right here, the wording already instructed us to find a sinusoidal function that models the height in feet of any rider who's on that, of any occupant who's on that wheel right here. So the height above the ground right there. So sinusoidal has to be either a sine function or a cosine function. So we have only two plotted data points so far, but now the question is asking us to come up with a sinusoidal function. So sinusoidal function has to be like this. If it's a sine, then it must go around a center line. I treat that as a center line. If it's a sine, then it has to start right on the center line. Halfway through first quarter, third quarter, it has to hit high, the highest point, 100, and hits low at the third quarter. But that doesn't look like the case right here, because we have a start here at the low, and then it ends at the low. So it looks like the sinusoidal has to go like this. At halfway, we have to hit the highest point. And at the quarter, we have to cross through the mid-height right here. And so our graph must look like this, according to the requirements. Okay, because the requirement here forces us to have a starting at a low right here. And so being one of the two sinusoidal functions right here, the sine cannot be in this case, because the sine starts right on the midline and swings up and swings down and back to the midline and swings back up to at the end of the cycle. But here, for our function here, we start low, we hit high at some point, right? And so that point has to be exactly halfway, okay, throughout our entire cycle right there, and then hits back down to that same low point right there at that complete cycle. So now I'm seeing this as a cosine function, but it's a negative cosine function. From our graphing experience, the usual cosine goes like this, okay, right through the center line, but now this one here is upside down, okay? And so in that way, I was combining the plotted data points step and fitting a sinusoidal graph right through the picture right here. Okay, and so now once we have fitted that, right, and we have come to the decision, it has to be a cosine. So now what you have seen in my earlier demonstration problem, I can write it as some coefficient. That's for the amplitude. And then cosine of A times the t minus the starting point plus with a constant k. This graph has center line at y equals 56, being exactly halfway between 12 and 100. This graph has amplitude being 44. The amplitude being 44 because the midline is here, the center line is here, it swings up to hit 100 by a total space of 44 and down by a total space of 44. And so that's why the amplitude here is 44. And so I can now partially complete my information. Now be aware that the graph for our function here is an upside down cosine. So with the amplitude now found to be 44, I must put that as minus 44 cosine of sum A times t minus c in parentheses plus what our center line was at 56, so plus 56. Okay. And from the graph right here, the given information was telling us that the complete cycle here of the whole rotation, that refers to periods. One complete cycle was given to be 5 minutes. 5 minutes. And then we did not choose our starting point in this problem, but we were given instead a starting point. So the starting point was given to be at t equals 0. So the start point was given as t equals 0. I am now going to bring this information that we have just found out into our the function. So here I'm looking at equating 2 pi over a. This is the general expression for any period of a sinusoidal function. That must equal 5. And that means solving for a from this equation, it leads to a must equal 2 pi over 5. And upon finding a equals 2 pi over 5, I can now put that value or substitute that value into for a right here. We're looking at y equals minus 44 cosine of 2 pi over 5 in parentheses t minus c, close parentheses, plus 56. Now with the given starting point t equals 0, I can substitute that into the starting point as designated here. And so our function now is completed as y equals minus 44 cosine of 2 pi over 5 times t in parentheses plus 56. And that is how we have completed our modeling function. And in this problem right here, we have a given starting point instead of being able to choose for one. So the height of any passenger at time t, some t minutes after a rotation, is determined by minus 44 times cosine of 2 pi over 5 t, okay, plus 56. And that's how I have come up with the modeling function. All right, and so now that we have found the modeling function for this Ferris wheel to be as concluded on the board earlier, now we can apply that to find the height for any rider or any occupants 2 minutes after boarding. 2 minutes after boarding. And so now recall that our function h of t equals minus 44 cosine of 2 pi over 5 times t plus 56. 2 minutes after boarding means, because again, the boarding point is the starting point t equals 0. So 2 minutes after boarding means t equals 2. All right, so in that case right here, that height we're looking for is simply just the height at time t equals 2. So I'm going to substitute t equals 2 into the function. So now we will come up with, in written form, minus 44 times cosine of 2 pi over 5 times 2 in parentheses, plus with 56. And again, let's keep all of the calculation here in radians. Okay, and on my calculator, minus 44 times cosine in parentheses 2 pi over 5, close that parentheses, times 2. Close another parentheses, plus 56. And that comes out 91.59674, and a lot longer. So in 2 decimal places, at 2 minutes after boarding, that occupant has come to the height being 91.6 feet. Rounding to 2 decimals, I was forced down to only a 0.6. But that was how I found the answer for that problem.